So we talked about in the previous lecture the discovery of the planet Neptune. Now let's talk about the planet itself. Because in the telescope, Neptune doesn't look like much. It looks like a very tiny blue dot. With good magnification, you see that it's not just a pinpoint like a star, it's just kind of a little round blue dot. And so I remember when I first was starting in astronomy, finding Neptune was actually kind of tough because it looks kind of like a blue star, and you have to kind of magnify a little bit to see that it's not just a dot. I mean, not just a dot, it's a little round disk. The blue is coming from the methane. So we got more methane clouds here than we did on Uranus. So Uranus was kind of a bluish green color, and then this planet just looks bluish. And so a good picture from an amateur astronomer here makes it look like just a little blue featureless ball. So that's what astronomers were expecting to find. Because after all, it's a long way from the sun, enormously far from the sun. Sunlight out here is so weak that you don't expect much atmospheric heating, not much atmospheric convection. By the time the Voyagers had passed by Uranus, we saw that Uranus was totally boring and featureless, and so we figured when Voyager 2 passed by Neptune, it would be pretty similar. So Voyager 2 did pass by. It passed by in June of 1989. And so I'd already been teaching astronomy by that point. And so we had talked about Neptune in class, and it was just like we didn't really have much to say about it other than, well, it's got more ammonia in the clouds because we could tell that from the spectrum, and we expected it to be pretty much a twin of Uranus. And then in June of '89, we had got our first views of it, and it was like, oh, that's not what we expected. So Neptune, again, 30 AU from the sun. And so, 30 AU from the sun is long ways. That means that sunlight is almost 1,000 times dimmer at Neptune than it is at Earth. It's about 900 times dimmer. And so that's very, very dark out there. That meant that they knew that when the Voyagers flew by, they'd have to take really long time exposures of everything that they looked at. And so it was also so far away, it takes light a very long time to get from there to here. So that means that it's about 4 hours of light time. So that means that when the signal comes back to us, when we get it, it's about 4 hours after the signal left. Well, that meant that you had to plan days in advance what you were going to look at, schedule the observations, program it into the spacecraft's computer so it would turn and face in the right direction, take the pictures. By the time it took the pictures and sent the signals back to Earth, and then we got around to analyzing them and sent a signal back to say, go look at something else interesting that we didn't know to look at, then the spacecraft would be long gone. It's going to be 8 hours round trip, and that's assuming no analysis even being done. And so and it was only in the vicinity for a day or so, so that tells you that we had to know in advance, so that we just got our best guess as to what to look at. The orbit is pretty circular. It's only 0.01 eccentricity, so that makes it a very, very circular type of orbit right there. It orbits about once every 165 years, rotates about every 16 hours or so. A lot of this we could figure out from observations from Earth. And so, again, through the spectral analysis. The size and mass, again, the size and mass are very similar to the size and mass of Uranus. Again, they're like twin worlds out here, and the composition of the atmosphere is mostly hydrogen and helium with a fair bit of methane in there. Okay. So, Uranus and Neptune, twin worlds. Neptune is a tiny bit more mass than Uranus. It's a tiny bit smaller, and that's in part because the extra mass means extra gravity, and the extra gravity tends to squeeze it smaller. So that's that it squeezes the atmosphere, which is hydrogen and helium, a little bit tighter, and so that's kind of what's going on there. But other than that, they are believed to be very much similar, except when the Voyager sent back pictures, instead of a featureless blue ball, they saw an incredibly active world. An active world that had faint stripes on it, had storms, had a large dark storm here with things swirling around it. They call it the Great Dark Spot right there. It's sort of a giant hurricane there. There's all these other little wispy white clouds. These are high-level clouds that make ice crystals, and they're floating around in the atmosphere and blowing around at very high speeds. In fact, the speeds here were phenomenal. So you have some of the winds would be supersonic winds. And so it was an amazingly active world. In fact, even just, from several photographs as the spacecraft was approaching, we could see changes happening in the planet. Again, they didn't expect anything like this. This is one of the most dynamic atmospheric sort of situations here. And so in a world that's so far from the sun, that solar heating should be doing nothing. None of this should be happening, they thought. And then what really was a surprise was not only was this great dark spot a hurricane the size of the Earth, but the winds up to 1,200 miles per hour, storms swirling, storms forming, dissipating, going away, kicking up stuff, ice crystals, and amazing. What was also amazing was it was emitting more energy than it got from the sun. Now, Jupiter does that because Jupiter is still doing Kelvin-Helmholtz contraction. Jupiter is still contracting a little bit and squeezing, and that's producing heat. Saturn does it because of that helium rain. And so now the question is, well, why is this world doing it? So what's going on here? And so this is a good question. Why is this world doing it? Because it's not big enough to get helium rain. You're not going to have the right temperature or pressure to do that, so that's not going to happen. And then the next question was Kelvin-Helmholtz contraction. Definitely not able to do that. And so it's not doing that. So what could be doing this? And so this was a huge mystery that they had. And so they're trying to figure out why. Why would it do such a thing? To answer why, we need to understand how the insides of these worlds work. And so we look at them and we say, well, Uranus and Neptune are pretty similar to one another. And so what's going on inside? Same thing. We think that the interior is going to be basically the same sort of thing. We have a core that's a mixture of rock and ice. Okay, we have a mantle here that is liquid ices. So this is squeezed water and methane and ammonia. The ammonia in there makes these salts that tend to make it electrically conducting. And then we have an atmosphere on the outside. The atmosphere on the outside is going to be hydrogen and helium for the most part. So just like with the planet Uranus, then we're going to find that at least half of this world is probably water. Okay, now again, this is water squeezed down to a state that is nothing like you're familiar with. So you might think, you know what water is. This is not going to behave like water as you know it because it is so highly squeezed, so highly compressed. And so it's going to behave a little bit differently. But again, it's going to probably behave very much like it does on Uranus. All right, so similar composition. We think Neptune might have a little bit bigger core than Uranus does. That's why it has a little bit more mass. That extra mass means that it squeezes the atmosphere a little bit smaller, a little bit tighter. Okay, so that's due to the extra gravity. But other than that, these worlds are very, very similar. Remember, we originally said we thought that Neptune formed a little closer to the sun than Uranus, and so that means it probably had a little bit more stuff in there with which to make it, a little more rocky things, and that's probably why the core's a little bit bigger. So there we have the basic structure of the worlds. Just like Uranus, Neptune has this really weird magnetic field that's highly tilted and highly eccentric. So it's off to one side and it's tilted almost to the equator. So this is almost the same kind of magnetic field that you have on Uranus. Now, when they saw the magnetic field in Uranus like this, they had all kind of weird ideas. One weird idea they had was that maybe we just happened to catch the planet as it's changing its magnetic field or flipping its magnetic field, and maybe instead of just like going away and reforming on the other side, it just slowly rotates over. That was one idea that they had, but it seemed pretty unlikely that you just randomly happened to catch a planet doing that. It's almost impossible statistically to catch two planets doing that. And so, now we have two that are like this, so that seems to make it like not at all likely. Second, the other idea they came up with is maybe some big thing slammed into Uranus, knocked it over, and left the magnetic field behind. That idea doesn't seem to make sense either. And so they were toying with that, though, until they found Neptune. Neptune's not laying on its side. Neptune is only tilted about as much as Earth is, a little bit more than Earth, but similar to what Earth is. So it's not going to be so weird of a tilt, and yet the magnetic field is still super tilted, just like it is on Uranus. So this suggests instead that there's something that's happening in this icy, liquid, salty mantle that's producing the magnetic field. And since both of these worlds have the same sort of way of making the magnetic field and the same similar interior structure, that would maybe explain why the magnetic fields look so much alike. Now, that would suggest maybe there's something happening in there that's unique to these two worlds. Now, we don't really know yet. We're still trying to figure this out. Remember, only one spacecraft has ever been there, a spacecraft that was launched in the mid-1970s. And granted, it took much longer than that to get out to the outer solar system. It took over a decade to get here to Neptune, but it was the only one launched mid-1970s using early 1970s technology. And without having anything going out here before, they didn't even know what to look for, so they just put generic sort of instruments on the spacecraft. Had we known what we were looking for, we might have put something different on there. So right now, we don't know why these two worlds had the magnetic fields that they do. But their magnetic fields, as I said, are very similar to one another and very different from the magnetic fields of other worlds. Again, one thing we don't know yet, still trying to figure out, is why everything but Saturn has a magnetic field that's tilted relative to the axis. Saturn's does not tilt relative to the axis. So that's yet another mystery. So there's several of these magnetic field mysteries that are going on with the planets in the solar system that we're still trying to figure out. The salty mantle, that's almost certainly what's causing the magnetic fields on Uranus and Neptune. But we don't really know exactly how or why it's making the magnetic fields the way that they are.